Good morning. Once again, welcome back to part 2 of ultrasound. Today we will be looking at the uses, right? Just some info first, resources that you can get from A-level Physics A2, right? Where the PowerPoint, the notes, the video will be there. If you got question, you can ask there, put a note there. And then you want to try out the past year paper. That one is notes, PowerPoint, video. This one, Physics, past PYP means past year paper A2. 2001 to 2010, topic by topic to practice, right? So that you're familiar what came out in CAIE. Or I can go to subscribe in YouTube. I can ask question there, or I can ask question in Facebook. Okay, let's go back to our topic for today. Okay, users, we are more interested in A scan rather than B scan. Right? The main requirement of syllabus, explain the main principle behind the use of ultrasound to obtain diagnostic information about internal structure. Right? So we want to obtain, the users is to obtain the image of the internal structure and learn what we have learned from part 1 to use all the formulas to do some calculation, show you what came out in the exam paper. Right? So part 1, we study about production, how ultrasound is produced. So ultrasound, we say any sound wave above 20 kilohertz, transducer, any device that converts energy from one form to another. So we will use the ultrasound transducer. Will convert the ultrasound into alternating current, or we can produce ultrasound. Transducer is a receiver and produce ultrasound. Piezoelectric effect, we say that a voltage will be generated across quartz crystal when there's a pressure applied, and the polarity on the crystal depends on whether it's compressed or stretched. And after that, we look at production of ultrasound. Okay, since there's no space there, you can draw picture there. In fact, you can draw on a full set paper to help you relate each part of the syllabus. You have a quartz crystal, we got silver electrode, and then we connect it to an alternating source. If we want to get ultrasound, then the alternating source frequency must be the same as the ultrasound frequency that we want. Okay, and after that, we look into what happened when the ultrasound meet a boundary. And what happened when the ultrasound, that is transmission, what passed through the boundary. And then as it enters the medium, what happened? Part of it will be absorbed, part of it will come out of the material. Right? And then we introduce the term acoustic impedance as Z, density of the medium, plus the speed of ultrasound in the medium. Then we introduce, this is just the original intensity. As it passes a boundary, part of it is reflected, part of the intensity passes through the boundary, we call it transmitted. And then this one allows us to calculate the fraction, reflection coefficient, and basically your IR is just your difference between the impedance, the acoustic impedance of two medium. Then we square that, that's all. And then I is just the total of them. Right? This formula usually will be given in the exam, but you need to know how to interpret them. So if you're a great difference, either Z1, Z2 is very much greater than Z1 or Z1 very greater than Z2. Right? So if Z2 is greater than Z1, that one can be considered as very small, negligible. So that one is also negligible. Z2 and Z2 cancel, it be 1. So it means there's no transmission. Example, air and skin boundary, all of it is reflected back. Now this is a fraction that is reflected back. 1 means all reflected back. nothing go into. So no point using such a air skin surface there, because no ultrasound will enter the body. We want the ultrasound to enter the body so that we can see the image of the structure inside the body. And of course, you can also think of it as when this is 0, what happened? When this is 0 means that these two difference is very small. Very small. 0 means all of it will pass through, or most of it will pass through. And absorption, we will use this formula. Right? This is the original intensity before it enters the medium. This is after passing through the medium. And there's the absorption coefficient. And then we can also calculate the thickness of the medium. That's the speed of ultrasound in the medium. That's the time for the ultrasound to go in and out. D is the thickness of the tissue. Right? We'll be using all this formula today, this morning. Okay, that's why we say if Z1 equals Z2, approximately equals to Z2, that one will be 0. So this will be 0. 0 means large transmission, it just pass through. Very little reflection. That's between the gel and the skin. That's what we want. That's why we put a gel between the skin and the transducer. Two techniques. We have A scan and we have B scan. Right? Well, we are interested in A scan only, not B scan. Right? A scan just gives us the thickness of the layer, which we would be interested how to analyze it. And B scan basically gives us the image of the part that we are interested in. And basically, B scan is a lot of A scan as well. A scan system basically measures the distance of the different boundary. Now we are interested in the thickness of the tissue from the transducer, with the transducer being held in one position. Right? There's a typical image on the CRO screen of A scan, right? Where we have that's where the pulse, right? The transmitted pulse. Remember, we are always using a gel as a surface there, and the transducer as a surface there, send in the ultrasound. If there's a fat, there's a muscle, there's a bone, and then there's the thickness of the muscle, and that's what we see. Right? This we will answer this question later on. Right? Where you are told that pi square is 1 cm. So it means that one small square is 2 millimeter. And this is where you send in as your pulse there. Okay? So as it meets the fat, right? The fat muscle boundary, that one, get reflected back. That's why it comes back. You lose some energy. So that's why the amplitude becomes smaller. And we can read the time as 2 square there. 1 square is 2 millimeter. 2 square is 4 millimeter. Right? Or 0.2 cm if you want. Right? 4 millimeter. And then we are interested in that thickness of the tissue. Right? That's your fat. Right? Muscle, you are interested in thickness of muscle. So that one will be your muscle and bone boundary. That one. Okay. So we are interested in that thickness later on. We'll look into that. So this one, examiner will only tell you that's the reflector pulse. There's also the reflector pulse. Just supposed to identify yourself, they will tell you what are the things that are involved. Right? And time-based is chosen so that all the information is on the same screen. We don't want this one to be outside, right? Or on the same screen. Okay, at the start. Explain the main principle behind the use of ultrasound to obtain diagnostic information about the internal body structure. Right? Basically, we send a short pulse ultrasound by the transducer, right? And the transducer is placed on the body with a gel, right? We don't want air, right? The gel is just the medium there. Then we have to explain at each boundary, right? What happened when you meet the boundary there? Okay, so some of it will be reflected. Right? This one, meet the boundary, that part will be reflected, that part will be transmitted. As the reflected pulse is picked up by the transducer, right? That's reflected, must go out of the skin. So transducer act as a receiver now. Signal is processed and displayed on the cathode ray CRO. That's what we see. That's the first one. Then we must explain how to find the thickness, time between the transmission. That's transmission. That's the reception, receive back of the pulse, give information about depth of the boundary between the speed, where speed of medium, right? That's the pulse that we send. That's the echo, right? For the first layer. Right? The speed of medium must be given here or known. Some extra point. The reflected intensity, right? The reflected intensity, amplitude square gives the intensity is smaller, gives information as to the nature of the boundary, what type of boundary that we made. Reflected pulse also meets boundary as it returns to the transducer. This causes sound energy of the reflected pulse to be lost, and energy is also lost due to absorption there. As it meets this boundary there, bone muscle boundary, get reflected. So when it goes through, it's going to be absorbed by the tissue, by the muscle. Then when it go reflected, returning to the surface of the skin, it also absorbed by the muscle. That's why energy is lost. Right? Intensity becomes smaller. Consequently, the echoes from deeper in the body tend to be low intensity, shown by the small amplitude. To compensate for this, the later an echo is received at the transducer, the more it is amplified before display on the CRO. Because if it's too small, you can't see it. That's why you have to amplify it. That's why we see a vertical line appears on the screen each time an echo is received. Right? Ours is a very simple case. Only one layer, two layer. Right? There can be many layers there. Then based on the X plate, it's adjusted so that all the reflections are seen on the screen for one pulse. We don't want this one to be outside the screen. We want all of this to be in the screen, then we can analyze it. Okay, we have completed. Let's go to worksheet. Try to do some example. If you got a worksheet, it's page 113 and get it from Facebook. Should be able to calculate. They give you some data. Use the data given to calculate the acoustic impedance of air and water. Okay. First, you must know the definition. For air, Z acoustic impedance equals to density of medium times speed of wave in the medium. Right? You can use C, you can use V, it doesn't matter. Then go to the table. Density is 1.2. Speed is 340. Calculate out. And after that, for water, same. Z is rho C. Rho is 100. C is the speed, 1,500. Calculate it out. And you get the answer. Using the speed of ultrasound, usually they will give you this formula. They won't give you this one. You are supposed to know how to interpret that. Using the speed of ultrasound and the density of air, and the acoustic impedance in air is 410. Use the data in the table. There's the table. To calculate the intensity reflection coefficient for air fat boundary. That's your fact. Air is given. So alpha, air, that's your Z1, air. Doesn't matter which subtract which. Ultimately, whether it's positive or negative, you square that, it becomes positive. Okay, so if that is your air, then Z2, your total fat, look at fat. Right? Fat. Your Z for fat is this one. Sorry, fat is this one. That one is muscle. This one is your fat. Right? One, you add them up. One is subtract. Take difference, square that. Or you can, and then the other one, you just add them up. So you don't want to square that after you do the calculation, then square the same thing. Get that? So this show you is almost 1. Almost 1. That means transmission is very poor, where most of it are reflected back. Should be able to interpret from the data. Then you want fat and muscle. That is your fat. That's your muscle. You take the difference and then you add them. Right? Take the difference, you add them up, square that, get this value. So this one tells us that it's almost 0. Almost complete transmission. And between muscle and bone, this is your muscle, this is your bone. Right? Take the difference between them. Right? Difference, square that. And you add them up, square that. Okay, and then you can use your calculator to calculate. You get 0.41. So that is good. 0.41. Right? There's transmission, there's some reflection. Right? This is called impedance mismatch. Poor contrast. Two of them almost the same. Very poor contrast. You can't see the difference in your picture. Right? So this is almost 100% reflected. This one is almost 2%. We just times 100. It's about 2% reflected. Explain the use of gel on the surface of the skin during ultrasound diagnosis. I can see from there. For the skin, it's not good. We want the ultrasound to enter the body. Then we can see the image of the organ in the body or the tissue in the body. We don't want 100%. We want a lot to enter. Right? Initially, we enter. So very little transmission of ultrasound at the air-skin boundary. Almost complete transmission at the gel skin boundary. That's the reason why we use a gel. It has the same, almost the same density as the skin. Okay? So if that is so, then when the wave travel in and out of the body, it doesn't get reflected. Suggest and explain one advantage of the use of ultrasound of frequency 1 megahertz rather than 100 kilohertz. Remember, larger the frequency, smaller the wavelength. Smaller wavelength, you can see greater detail. Okay? Wavelength of that is shorter than that one there. So greater detail is possible of what we want to see inside the body. Okay, I think we won't bother about this one. We will try this one later on. Let's try to analyze this one. An ultrasound pulse is transmitted into the body of a patient. The pulse is partially reflected at the fat muscle boundary and then muscle bone boundary. The reflected pulse are received back at the transmitter and are displayed after processing on the screen of the cathode oscilloscope. The trace is shown. That is a trace. Right? They tell this is a transmitter. That means it's the one sent out by the transducer. This one is reflected, received back by the transducer, meet a boundary, then it returns. This one go back into further boundary, come back to the surface there, and then that's what you receive after a certain time. Okay, so it will be identified as your fat muscle. The first one is your fat muscle. The next one is muscle and bone. Right, and that is your time-based given. And you should be able to read. Right? Pi square is 1 cm. So one small square is 0.2 cm or 2 millimeter. So 2 square is 4 millimeter. Right? And then, as I said, it can drop. Start from this 0, 5 square is 1 cm, another 5 square, 1 cm. Right? So there are 1, 2, 3, 4, 5 cm, and then 1 square. Right? 1 square is 0.2, so it's 5.2 cm. Okay. Determine the thickness of the layer of fat given that the speed of ultrasound, in fact, is that. So go back to the picture there. There's the layer of fat there. That is the layer of fat. Right? That time there will give us the thickness there. So it's 4 cm. So trace length is 4 millimeter. Distance, right? Remember the distance is to and fro. Pulse go from the surface to the fat, reflected back at the boundary and go to the surface. So that one double the distance. So distance is speed times time. Speed, that's the distance on the CRO times your time base. Right? So speed you are given, that's the speed. That's why we convert it, right? 4 millimeter to 0.4 cm. And then there's your time base that we use. Right? So either you can write in meter or 5.8 millimeter. And we have to divide by 2 to get the thickness because it's traveling to and fro the pulse. Same calculation. Yeah, you have to be careful you're reading 5.2 cm. Distance is speed times time again. That's the speed in the muscle. And that's your 5.2 cm. Okay, and refer back. We are interested in that distance, that thickness. So it's 5.2. Right? So there's a speed, that's 5.2, and there's a time base. Right? Calculate the time. So you get that? Oh, 8.2 cm. Then you need to divide by 2, find the thickness. Okay, explain briefly the use of ultrasound to obtain diagnostic information about the internal body structure. Always keep in mind the number of mark is from 2004 November. I think when you come to ultrasound, it's either you calculate or you just memorize this. It may come out. Very rare. Occasionally it may come out. So pulse or ultrasound transmitter, you place a transducer with a gel on the skin and pulse or ultrasound transmitter. The pulse is, tell what happened to the pulse. Pulse is reflected from boundary and receive a surface, and receive a surface is processed. That's a 3 mark already. Time for the pulse to return, give the depth. Right? The time, what does it give? What does it indicate? It indicate the depth of the boundary, or the thickness of the boundary. And then reflected intensity give information of the nature of the boundary. What type of boundary they are meeting? Okay. Sometimes they are kind, they may give you that equation. Right? Variation of intensity of the parallel beam of ultrasound with thickness X measured in meter. A muscle is given by the equation, that one there. I know it's the initial intensity. Calculate the fractional intensity I over I naught transmitted through the muscle of thickness 5.5. You are one who like to see picture, you can draw. That is your thickness of the substance or muscle. In this case, is muscle. That's why you enter. Before you enter, that's why come out of the muscle. For the fraction, we are just using the formula. Right? Remember, your total X is in meter. This is cm, so you have to convert that to meter. Right? That means this is adjusted already. This one is per meter. That's why you have to change it to meter and use your calculator to calculate out. Having traveled through muscle, right? That's your muscle. The beam is reflected from the muscle bone boundary. At this boundary, 35% of the incidence reflected. Remember, 35% is at this boundary there. Calculate the fractional intensity I, Y naught that's received back at the transmitter. So when it comes to this type of question, you have to keep in mind what we have calculated previously. This one, this is the absorb. Okay? There's a fraction absorb as it goes through here. Then you must keep in mind as it goes through surface there, the gel, so it goes straight through, it will be absorbed, reflected, one reflection, and then there's another absorption. Right? That means two of this value. Okay, so as it enters, there's a gel there. Usually they won't tell you. You have to assume there's a gel there, and then it goes straight through, no loss. And as it goes through the medium, it is absorbed. That's why we calculate this one, fraction absorbed. And at this boundary, bone and muscle boundary is reflected back. Then it is absorbed again. So that's why we have two absorption coefficient, and then there's one reflection. Right? Divide this one by 100. No need to show working. If you want to refer to lecture how I get you the formula, but you just use a formula and calculate out. Okay, two absorption. That's why you got 0.28, 0.28, and one reflection at the bone muscle boundary, which is that one there. Okay, you can see quite a popular question. Explain the main principle behind the use of ultrasound to obtain diagnostic information about internal parts of the body. We have done that. Pulse ultrasound sent by transducer, pulse reflected at boundary or boundaries and detected at surface by transducer. The signal is then processed and displayed. Time between transmission and receipt of the pulse give the information about depth of boundary. Okay, I'm going too fast because it's almost the same. We have done that before. Refracted intensity give information as to the nature of the boundary. Okay, calculation is a bit different now. Data for acoustic impedance and absorption attenuation coefficient, that one, attenuation coefficient, has an acoustic impedance Z of the muscle and bone is given. The intensity reflection coefficient is given by the expression. This one you are not supposed to memorize it. They will give you. If they in the syllabus they get recall and solve, then you have to memorize it. If they didn't say recall, then they will give you. But it's no harm to memorize it. Then you know how to use it. So the intensity reflection coefficient is given by that. The attenuation of ultrasound in muscle follow a similar relation to attenuation of X-ray in metal. The parallel beam of ultrasound eye, as parallel beam, enters the surface of the layer of muscle. That's your muscle, thickness 4.1 cm. That's your bone. The ultrasound is reflected at the muscle bone boundary and returned to the surface of the muscle. Right? Turn back there. Reflection there. Calculate the intensity reflection coefficient of the muscle bone boundary. This one. Okay, so go and look at acoustic impedance at the muscle and bone boundary. We want the reflection here. Then use the formula that's given. Right? The coefficient Z2 minus Z1. It doesn't matter which minus which. Ultimately, you square it becomes positive. You can take this one as Z1, that one is, sorry, this one is Z1, that one is Z2. Okay, so same thing is numerator, take the difference. Denominator, you sum them up. And then after the calculation, you square them. Get this value. Fraction of the incident intensity that is transmitted from the surface of the muscle to the surface of the bone. Okay, that one we are interested in the absorption. Right? That's the formula you need to memorize, the fraction. And then let's look at the equation to review what is given. Right? There's your 23 there. The equation is not given. There's a muscle. We are interested in the absorption in the muscle, so we use the absorption coefficient in muscle. Right? I think they have not given you the formula, so yes, we're expected to memorize the formula maybe. Okay, So that is the absorption coefficient in muscle per meter. So that's why we will have to change the thickness to that thickness there, cm to meter. And use our calculator to calculate out. Okay. So we are interested in, let me just get the picture and we can see what is happening. Okay, let's just get the picture, then we can visualize what is happening. Right? There's the incoming ultrasound. Remember, there's a gel there, so you don't have to worry about the reflection at the surface there. Just consider 100% transmission. Right? They've calculated the absorption here. The intensity in terms of I is where you send it in. That's received back at the surface of muscle here. Right? So you are supposed to remember, as it goes in, there's one absorption, then there's one reflection that we have just calculated there. Right? This is the absorption. Reflection is the before the equation. Then after that, as it returns, there's another absorption there. So there's your 0.3. There's your reflection. And then there's two absorption. 0.39 times 0.39. And there's the intensity entering it. Right? They don't expect you to go and derive the formula. Just remember that this is absorption. And then this value is the reflection at this bone muscle boundary. That's what we get. Right? Very low intensity. Okay. And see anything else that we want to do. I think that's about the end of the question. Don't bother. Most of it are just repeating. So we will end the question here. If you got any question, you can follow on Facebook or you can subscribe in YouTube and then you can ask a question there. Try to answer you. So I'll stop here. For those want to try more questions, you can download my PowerPoint or my notes. Thank you for your time.